I welcome you all to another video tutorial session on finite element procedure for solving structural engineering problems. In this video, we are going to use the finite element procedure to solve a continuous beam system using the MATLAB program by applying the finite element procedure. The problem is shown on the screen. It's been 2 to 3 days since I produced my last video. In my last video, in my previous videos, I dealt with one-dimensional problem and source problem, both 2D and 3D problem. So today I'm moving to another topic in finite element analysis, that is application of the finite element procedure for beam system. We're solving a two-span continuous beam in today's tutorial video using the MATLAB program. I also intend to solve this particular problem on the ANSYS software. So in my subsequent video, I'm going to solve this particular problem on the ANSYS program, and in those videos, I'm going to analyze this. This beam system by using three methods. I'm going to analyze this problem using the one-dimensional method in the ANSYS program, using beam finite element, one-dimensional beam finite element. I'm going to use that method. I'm also going to use the two-dimensional method in the ANSYS program to analyze the beam. In the two-dimensional method, we use plate elements to analyze our beam. So I'm going to show you how you use plate elements to analyze your beam on the ANSYS program. We're also going to so this is a slide for the 2D beam analysis of continuous beam system with ANSYS. We're also going to analyze the beam using the 3D finite elements on the ANSYS program. So there are three methods of analyzing beam on the ANSYS program. I'm going to show you how to analyze beam using these three methods. Using the 3D finite elements actually an overkill for the method is an overkill for beam problem with just one material. The 3D finite element is effective for analyzing composite material like concrete, where you need to model your concrete and reinforcements together. That is the problem in which the 3D finite element procedure, the 3D finite element in ANSYS is better suited for, but I'm going to show you how to use the 3D finite element method in the ANSYS program to analyze beam problem of this nature. Also, in my last video, I'm going to also explain the concept of symmetry in beam system. So, like the problem shown here, we have a three-span beam, but the beam is symmetric both geometrically and by loading. You can see at this point, what is on the left-hand side and what is on the right-hand side is the same. The shape is the shape is the same and the loading are the same. So this problem is symmetric. So we can just consider half of the beam problem and analyze it. I'm going to explain this concept in my last tutorial video on under finite element procedure for beam system. So I'm going to cover a lot under finite element procedure for continuous beam system. So let me go back to my first slide for the beam system. So in this video, I'm going to use MATLAB to solve this problem. We're going to solve this problem using the finite element procedure by applying the MATLAB, using the MATLAB program. What we have on the screen, we have a two-span continuous beam with different type of loading on the span. We have uniformly distributed load of 12 kilonewton meter. We have 10 kilonewton load. We have 8 kilonewton load. We have 6 kilonewton load. We have a two-span beam. First span is from node A to node C. Second span is from node C to node F. We are told that the flexural rigidity of this problem, the flexural rigidity is EI, is defined by EI, is equals to 100 times 10 power 3 kilonewton meter square. So EI is actually the product of the Young modulus and the moment of inertia of the beam section. E is the Young modulus, I is the moment of inertia of the beam section. So this product is referred to as flexural rigidity, and it is equals to 100 times 10 power 3 kilonewton meter square. We're told that there is a settlement at the support, at support C, a settlement of 4 mm. So we are going to consider this 4 mm in our finite element calculation in this tutorial video. So now, the first thing we need to do when we have a beam problem, we need to model the problem into finite element model. We need to define the finite element model for the beam system, for this continuous beam system, and I did that in my next slide. So for this continuous beam system, this is the finite element model I'm using to solve the problem. There are actually two ways of defining the finite element model for this beam system. I can define the finite element model by dividing this problem into 5 finite elements. The part between node A and node B is one finite element. The part between node B and C is another finite element. The part between C and D is another finite element. DE is another finite element. EF is another finite element. So I can decide to divide this define the finite element. I can decide to define the finite element model for this problem using 5 finite elements, but doing that makes the calculation very cumbersome, very difficult. So instead of me dividing this problem into 5 finite elements, I can just decide to consider the part between supports as my finite element. I'm not using the salient point, that is point of application of load, to divide my finite element. I'm only considering my point of support. So because this problem has 2 span, I choose to divide my this problem into 2 parts. The first finite element between node A and node C, and the second one is between node C and node F. So length AC is my first finite element, length CF is my second finite element. So I can solve this problem using just 2 finite elements instead of using 5 finite elements. So that is what I have here. You can see the finite element model. It has 2 components. The green labeling with triangle denote my element numbering. So this is element 1. This is element 2. Element 2 is between node 2 and node 3. Element 1 is between node 1 and node 2. So once we have defined the number of our finite elements, we also need to number our node. So this problem, we have 3 nodes. So you can see node 1, node 2, node 3. I number from left to right. Each node of a beam element has 2 degrees of freedom. At each node, we have a vertical degree of freedom and a rotational degree of freedom. You see 2 degrees of freedom at each node. At node 1, you see a vertical arrow and you see a rotational arrow. The vertical arrow I denoted my first degree of freedom. The rotational arrow I denoted my second degree of freedom. We do this for each node. For node 2, you also define the degree of freedom. The third degree of freedom, the vertical degree of freedom at that node. The rotational is my fourth degree of freedom. 5, 6. Note I number my vertical degree of freedom. I always number my vertical degree of freedom before the rotational degree of freedom at each node. So this problem has 6 degrees of freedom. From, you can see 1, 2, 3, 4, 5, 6. So you define your degree of freedom for the problem in this manner. Next, we also need to define our arrow direction. And for beam problem, it is best practice to denote your arrow of direction pointing from left to right for each element. For element 1, you can see my arrow head pointing from left to right. For element 2, you can see my arrow head pointing from left to right. For element 1, because my arrow head is pointing from node 1, that means node 1 is my start node for element 1 and node 2 is my end node. For element 2, this element here, the arrow head is pointing away from node 2. Node 2 is my start node of element 2 and node 3 is my end node for element 2. So we use the arrow head direction to denote which is our start node and which is our end node. We're also going to consider, we're not going to forget this 4 mm settlement at node 2, which is stated in the problem. So we're going to consider this 4 mm in our finite element analysis. And we are also told that the flexural rigidity EI is equals to this value here. So I'll move to the next slide. After we have defined our finite element model, we just define it using just 2 finite elements. The next thing we need to do, we need to compute the local stiffness matrix for each of the finite elements. And the local stiffness matrix for a beam element is given by what you see here. This is the local stiffness matrix for a beam element. Just like the one-dimensional problem and its source problem, the one-dimensional finite element and its source finite element, they all have their local stiffness matrix. The beam element also has its own local stiffness matrix, which is defined by this. You can see EI divided by LE cube multiplied by this matrix. EI is the flexural rigidity, where E is the Young modulus, I is the moment of inertia, LE is the span of that finite element, the length of that finite element. So this multiplied by this matrix gives our local stiffness matrix for each of the elements. Let me send this to the back. So let's take this for example. Let's take this for example. I need to erase this. Sorry. Let's take this for. Let's say we have this finite element, labeled finite element 1. It has 2 nodes, node 1 and node 2. Each node has 2 degrees of freedom, 1, 2, 3, 4. And I forgot to put the arrow direction. It's very important you specify the arrow direction. Say the arrow direction is pointing from left to right. It means that node 1 is my start node, node 2 is my end node. So because of this, when you are using the local stiffness matrix, because the arrow edge is pointing away from node 1, we pick our degree of freedom at node 1 first before the degree of freedom at the end node. So that's why we have it in this we have the numbering in this manner: 1 2 3 4, 1 2 3 4. Assuming the arrow edge was pointing in like in this direction, so that node 2 is our start node, node 1 is our end node. So the numbering will actually be 3 4 1 2. Also in the column direction, 3 4 1 2. So we need to understand like how to denote how to number local stiffness matrix for the beam element. So it all depends on the arrow direction you choose for each of the elements. I will move to the next slide now. So because we are going to be using MATLAB to solve our finite element problem, this is the local stiffness matrix for a finite element. Because we are going to use MATLAB to solve this problem, I define a function that can compute the local stiffness matrix of the beam of a finite element on MATLAB, and is written as this: function T1 equals to beams open bracket L comma EA. So you see the function, the name of the function is beams. When I enter two input variable L and EI is the flexural rigidity. L and EI, L is the length, EI is the flexural rigidity. Once I enter these two input variable and I run this code returns an output variable T1. This T1 represents my local stiffness matrix. I can see the T1 represents my local stiffness matrix. I see the T1 also written here, and it's defined as this. So this function here helps us to calculate our local stiffness matrix. I actually ran the code, like use this function on the command window. I entered 7 as my input variable, 7 as the length of the finite element, this value as the flexural rigidity. Once you enter these two value, you can compute your local stiffness matrix. So this is our local stiffness matrix. So this is done very, very quickly and very, very neatly. So this is how this is the procedure we are going to use to compute our local stiffness matrix for our beam element on MATLAB. Next, after we have computed our local stiffness matrix, we then we do what we always do. We assemble the local stiffness matrix into a global stiffness matrix. So after we've assembled the global stiffness matrix, we might need to modify it with our support boundary condition. After that, you define your force vector, and this slide explains how we define force vector for a beam for a beam finite element. So consider you have a beam finite element between node 1 and node 2. This is a beam finite element. This one is the node number, node 1, node 2. The length of the beam element, the length of the finite element is LE. The load on the beam element is P. What is important here actually is this force vector here. And I just want to explain the notation. That is what is actually important here. Because the force is pointing upward here, you can see how will I put it? You can see the value, how will I put it? Like this PLE, there are four this is the force vector. Okay. Before I explain that, we have each finite element we need to produce, we have a force vector. each finite element will have a force vector, which is a 4 by 1 vector, and this for each finite element there might be like an external load on the finite element, or there might not be any external load. For this finite element, we have a uniformly distributed load pointing upward. So we need to convert this uniformly distributed load into an effective nodal load. So for a uniformly distributed load, to resolve the load into effective nodal load, each nodal load will have two forces: vertical force and moment. So for this UDL, for this uniformly distributed load P, the vertical load, the vertical effective vertical load will be PLE divided by 2, where LE is the length of the finite element. Also the same thing at node 2, PLE divided by 2, where you see where you sum the two, you get PLE, which is actually the resultant of the load on the finite element. The resultant of the load on the finite element is P times LE, and when you add these two, you get P times LE. So the load is just shared equally between the span. Also for the moment, the effective nodal moment is given by these two values. You don't need to worry about the positive, negative. Just know the magnitude. That's what is important. So we have 4 components, and these 4 components is actually what is arranged in this force. Actually, what is arranged in this force vector. The first two is the effective nodal node at the start node. Say this is the start node, node 1. So this PLE divided by 2 is the first component. The PLE squared divided by 12 is our second component. The third and fourth part of the force vector is the component of the end node, that is node 2. The PLE over 2, this component here is so rough, I need to clean. This PLE over 2 is this value here, and this is this value here. So I didn't talk about the negative and positive sign, direction. What I want you to understand, which is actually very important, is that because the force is, this UDL is pointing upward, you should note something, that this is positive, this is positive, this is positive, and this is negative. If the force is pointing downward, say we have a span, this is a span, and we have a uniformly distributed load on the span pointing downward, not pointing upward, and that load is P, the direction will change, and this will be negative, 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 and this will be positive, but the magnitude will be the same. In our structure, in common structure analysis problem, for beam problem, we never have load pointing upward. This is just for explanation. Our load is always pointing downward. So this is what you need to memorize. Like the magnitude, the first component is negative, second part is negative, the third part is negative, the fourth part is positive for load pointing downward, and our load is always pointing downward in beam problem. So this is, you also know that the first 3 will be negative, and the last component will be positive. But this is actually what it looks like when the load is pointing downward. We have a vertical force here. We have a vertical force here. I think we have a moment force like this, and a moment force like this. And because this load is pointing downward negative, because this node, the vertical load at this node is also pointing downward, it is okay. Sorry, this first, the load here is this first part is this negative, and the vertical load here is pointing downward, so this is negative. This load, the moment is clockwise, so clockwise is like negative. That is sign convention. Clockwise is negative. Here, for the second node, which is given by these two parts, the negative stands for the vertical load, which is pointing downward. The positive stands for this moment. But what is important is that in beam problem, you always have minus, 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 positive, because the load is always pointing downward. But when the load is pointing, in exceptional cases, when the load is pointing upward, just know that it's also very simple. You just need to know that to be positive, 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 negative. So this is what, knowing the magnitude of the nodal force and just attaching the plus or minus to the magnitude is what you need to understand on defining force vector for beam problem using this finite element procedure that I'm explaining in this video. So this is for UDL, and these are the equivalent. This is the magnitude of the equivalent nodal load. But for other load type, what is the magnitude of the load? You can check this on the internet for other load type. But I actually have an image that shows the magnitude of the load for other load type. So let's say we have a point load P that is close to this support. The distance from the left support to the load P is A, and we also have a span B from the load to the right support. So the MA, MB is the moment, the equivalent nodal moment at the node. MA is the equivalent nodal moment at node A. MB is the equivalent moment at node B. Also, we have reaction. We have the reaction formula, as in the effective vertical force is given as an RA RB, and the RA is given by this formula, and RB this formula. So we have this for different loading. We have for point load, we have for moment load, we have for uniformly distributed load, which is what we have in our PowerPoint slide. You can see the MA, MB, RA, RB. So you just need to look for a table like this on the internet to define the magnitude of your load and assign this sign the way I explained to you on the PowerPoint slide. So say we have partial load, you can use this formula to compute the magnitude of the nodal load. Say we have a varying load, we can use this formula. Say we have an easier load, we can use this formula. So you should look for this on the internet, or you can take an image of this and store on your computer somewhere. I'll go back to my PowerPoint. So now I'll move to the next slide. So for our problem, for this problem, how do we compute the equivalent nodal load for our problem? We have two span, and in this slide I computed the effective nodal load for each of the finite element for the two span, each of the finite element. So this is the equivalent nodal load calculation for the first finite element, like this. Sorry. Let me erase this. This is our element 1 here. This is our element 1 here, and this finite element, the load on this finite element is the uniformly distributed load, 12 kilonewton load, and the 10 kilonewton load. So we need to determine the effective load of the effective nodal load of these two forces on the finite element. For element 2, we need to determine the effective nodal load of the 8 kilonewton load and the 6 kilonewton load on element 2. That's what I did on this slide. This is for element 1. You can see 10 kilonewton load and 12 kilonewton meter load. So what you need to do, you divide the load into two, as in you define each node separately. Like this span, I'm considering the 12 kilonewton per meter load. This span, I'm considering 10 kilonewton load. So you find the equivalent nodal load of this problem. So is defined as this. The equivalent nodal load you can see is defined as this. Once you use once we use this formula, as in this formula MAMB RB for the uniformly distributed load, we get like the vertical load as 42 kilonewton, the moment as 49 kilonewton meter at this node, and the same thing at the end node. So this is for the uniformly distributed load. For the point load, we use this formula, we use the first rule, this formula, this P, this point load P with there is at a distance A from the left hand support and distance B from the right hand support. So we use we use this formula over here where my cursor is hovering on. So we use this formula to compute the equivalent nodal load. And if we should do that, we get our vertical load and our moment load at this node as this and this node as this and this. So we need to add this component and this component together. So I'll add 42 plus this. It gives 48.061 kilonewton. Let me zoom. Also, for the moment, 49 plus this gives this value here. At the second node, at this node, 3.9 something plus 42 gives this value here. For the moment, this load, this 49 kilonewton meter plus this value here gives this value here. So once we have evaluated this is our equivalent. What we have here is our equivalent nodal load for the finite element. So you write the force vector. You can see P1 is the force vector for this finite element, and what we need to do, the arrow direction is always pointing from left to right. So this is our start node. So you write the vertical load first before the moment load. So I'm at this node. My vertical load is 48.0641. So I have this value here. My moment is this value. I have this value here. My force at the other node, my vertical load is this value here, which I have here, and my moment is this value here I have here. And I tell you, because I told you in the previous slide, because the loads are pointing downward, we use negative, 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 positive. As simple as that. So this is how you define force vector for beam problem. We do this for the second span also. For the second span, we have two external load on the second span. So you break them into two, this part and this part. So the equivalent of this 8 kilonewton load is what you have here. You use this formula here, this on the first row. and the equivalent of this 6 kilonewton load is what you have here. So you add these two together to get this, and you write out the first vector is defined as P2, and you write the magnitude out, and you attach your sign to it, minus, 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 positive. So this is how we define the local force vector for our finite element in our model, for our beam finite element. So after you have done that, we can now find the inverse of our global stiffness matrix and multiply by the global force vector. We also assemble the force vector. We assemble our force vector to a global force vector, and the PS here is representing our global force vector. This KS is representing our global stiffness matrix. So the inverse of this multiplied by this force vector will give us our displacement. I'm denoting ds as my displacement quantity for our finite element problem. So once we calculate this displacement quantity, we can now compute the reaction component for each finite element. The reaction component for each finite the reaction component is a 4x1 matrix. For a finite element problem, you have is a 4x1 matrix. The first two components is the reaction force at the start node. The last two is the reaction force at the end node. I'm going to explain all this in my next video. And this reaction component is equals to Kk multiplied by this matrix minus Fk. Here, Kk is the local stiffness matrix of that element. Dsk is the local displacement vector gotten extracted from this ds. When you get ds, you can extract this local displacement vector from this calculated vector. This Fk is our force vector. It's our local force vector. Like in this slide, I actually define it as P, not F. P1, P2. So P minus Pk. So we're going to move to the MATLAB working environment now, and I will show you how it is done on the MATLAB program. But before I go to the MATLAB program, when I did my calculation in the MATLAB program, I got like the R1 is like my reaction component for each finite element. I got this 4x1 matrix. The first two parts is the reaction component at the start node. The last two parts is the reaction component at the end node. So this first component for the 3.13 is the vertical force at the start node. The second is the moment. The third is the vertical force. The fourth is the moment. And we can see that like this is the reaction component for finite element 1. You can see I have for 3.138 kilonewton here, and the same thing with what I have here. I got this result from another program called StatPro, and you can see that the results are identical. This is shear force diagram, and you can see that the first component here is for 3.114, and I have similar value here. The moment the second component 0 is the moment is the value of the moment at the start node. I can see the moment here is 0. This 50.8662 is the value at the end node, the vertical reaction at the end node, which is given as minus 50.86, which is what we have here. And what we have here is our moment value, minus 32.0637, which is similar to this value here, 32.04. I did the same thing for, I think, the other span. You can see this 10.369. You see similar to this. You can see this 32.0637, similar to this. You can see You can see 3.6306 similar to this, and you can see 0 similar to this. So you can see that the result is the finite element result is very accurate when compared with results from other software programs. So now I'm going to move to the MATLAB program now. This is the function we use to create our local stiffness matrix I showed you on my slide. So this is the live script which I'm going to use to solve the problem. Coming, I should copy this and put it here. Okay, so this is our finite element model. That's the first thing you do. You define your finite element model. So, after you have done that, you compute your local stiffness matrix, which is what I want to do here. So to compute your local stiffness matrix, I'm using this function, and I need to know the length of the function and the flexural rigidity. And we're told in the question that the flexural rigidity EI is given by this formula, 100 times 10 to the power 3 kilonewton meter square. The unit I'm using for my calculation, the length meters, the length is meters, the force is Newton. So this value will be 100 times 10 to the power 6 Newton meter square. I change this K to 1000. So 100 times 10 to the power 6 Newton meter square, because my unit is Newton. I'm not using kilonewton. So this is the flexural rigidity value. And we also need to consider, let's not forget the 4 mm settlement at node 2. We'll consider this settlement while we're solving the problem. So for element 1, the first element, I define the length of the finite element 1 as 7 meters. I use the function, I enter L1, enter L1 as the length of the finite element. I enter this value. Okay, I'm working in kilonewton. My unit for force is not Newton, it's kilonewton. So that's why it is 100 times 1000, not times 1 million. So that's why it is 100,000 here. My unit for force is kilonewton. So once I enter this two, this value here is my flexural rigidity. So once I enter these two input variable and I run the code, my K1, I'm defining my K1 as my local stiffness matrix for element 1. K1 is computed. Same thing is done for K2. The length of K2 is 11 meters. It's seen here, 11,000 mm, 11 meters. So 11 meters, K2, you enter the two, you use the function and you enter the two input variable. L2 is 11 meter. This is the flexural rigidity. They have the same flexural rigidity. Once you write this MATLAB line of code and you run it, your local stiffness matrix for element 2 will be defined as K2. So now after we have defined our local stiffness matrix, we need to assemble our global stiffness matrix. And I'm denoting our global stiffness matrix in this exercise as K. And as we normally do, we create a base matrix, a zero matrix. And because our problem has 6 degrees of freedom, the size of our global stiffness matrix will be a 6 by 6 matrix. So that's why my base matrix is a zero, that's why my base matrix is a 6 by 6 matrix. Let me display it, let me run it. I see my K matrix. I see this MATLAB line of code creates a 6 by 6 matrix. Then I add K1. I've explained how to add matrix to base matrix in my previous videos. I'm not going to do the explanation again. The K1, the degree of freedom on K1 is between 1 to 4. So that's why here is 1 column. That's why the numbering is 1 column 4. That is 1, 2, 3, 4. 1 column 4, comma 1 column 4. This matrix, what you write here, you write on the right hand side plus K1. This is the same thing for K2. For K2, the degree of freedom numbering is 3, 4, 5, 6. The degree of freedom of element 2 is 3, 4, 5, 6. So that's why it is 3 column 6 for K2. This 3 column 6 means 3, 4, 5, 6. So you write this on the left hand side, you write this on the right hand side, you add K2 to it. If you run it, you see K1 added to the 0 matrix in this position at position 1 to 4. If you run this one, the K2 is added at this position here. So this is the global stiffness matrix for the problem. Now we need to modify the global stiffness matrix because we cannot invert this matrix. This is a symmetric matrix. It's symmetrical, so we cannot invert it's singular. So we cannot invert. It's symmetric and singular. So it does not have, you can't get the determinant of this matrix. So we need to modify this global system matrix so that we can use it in our calculation, and you modify it using your support boundary condition. And for our problem, let me go back to the PowerPoint. For our problem, we have support degree of freedom at node 1. You can see we have a pin support at node 1. The moment is free to rotate. So one has degree of freedom, one has support in the direction. Also, degree of freedom 3 has support. You can see there's a roller support there. So degree of freedom 3 has support. Also at node 3, we have a roller support. So 5 has support. So 1, 3, 5 has support. So 1, 3, 5 has support degree of freedom. The 2, 4, and 6 are free degree of freedom. They are free to move. So 1, 3, 5 are our support degree of freedom. So that's how we define the support degree of freedom. I'll go back to the MATLAB program. So what we need to do, since we're using a penalty approach, we need to define a large stiffness, which we'll use to modify this global stiffness matrix. And that large stiffness is taken as the maximum value in this matrix multiplied by 10,000, as we normally do in one-dimensional problem and our source problem. So this function here, this mass function here, actually gets the maximum value in this matrix, and I multiply by 1,000. So C is the last stiffness which I want to use to modify this global stiffness matrix. So at degree of freedom 1, 3, and 5, that are my support degree of freedom. I will add C to the global stiffness matrix. So because we have support at degree of freedom 1, 3, and 5, so I'll add C to 1 column 1, to 3 column 3, and to 5 column 5, 5, 3, 3, 1, 1, 3, 3, and 5, 5. So this MATLAB code is adding C at this position. So once you write this code and you run, C is added to the K matrix at this position. You can see the value has changed from 0.349. It has changed to 9.3407. I also add C to position 3, which is this here. I add C to position 5, which is this here, 5, 5. So I've modified the matrix in this manner as such. So the next thing you do after you've modified the matrix, you define your force vector, and I've already explained how you define your force vector, and I've even calculated it in my PowerPoint presentation, so I'm not going to explain it again. So that's the force vector for each element, you define it, and the force vector for each element is a 4x1 matrix, so which is given as this. This is the first part, this is the second part, this is the third part. I actually did the calculation and I just put the value here. And you will see, I should go to my PowerPoint. We'll go to my PowerPoint and see the value. The first part is 48.06, which is what we have here. If we should do this arithmetic calculation, minus 42 minus 6, we have minus 48.06. Here is minus 49 minus 9.7. You have like 58 point something, which minus 58 point something, which is what we have here. The third is minus 54 minus 45.93559. We also have it here. If you add these two, you get minus 45.935. You add this one, you get 56. We should have 56 in our PowerPoint presentation. So this is for the first element, this is for the second element. So I just entered this value. I did the calculation manually and I entered the value in the on MATLAB. So this is for element 1. This P2 is for element 2. So these are the force vector for the two finite elements, P1, P2. So I've defined it now. What you need to do, after you define the local force vector, you need to assemble the local force vector to a global force vector. It's actually not a matrix, it's a vector. So the local force vector I'm defining as F. So I create a base matrix just like the global stiffness matrix. So 6x1. The size is 6x1 because the number of degree of freedom in this problem is the number of degree of freedom is 6. That's why it's 6x1. It's a vector, so that's why it's 6 column 1. So if I should run this, this is what you see. You see 0, see a 6x1 vector. So this is 6x1 vector. So I'm going to add P1 to the first vector and P2 to the first vector. Imagine P1 at position 1 to 4, because for finite element 1, the degree of freedom attached to finite element 1 are 1, 2, 3, 4. This 1 column 4 means 1, 2, 3, 4. P2 3 column 6. This 3 column 6 means 3, 4, 5, 6. So P2 is added at 3, 4, 5, 6 of this matrix. So once this is, let me remove the, this is what we have. And see P1 added to the 1, 2, 3, 4 of F. And P2 added to 3, 4, 5, 6 of F. So this is our global force vector. So once you have done this, now this is where we need to modify our force vector with a value, because we have settlement. Once you have settlement problem, you need to modify your force vector, and you do this, this is supposed to be plus, not minus. It's supposed to be plus. You add the last stiffness, which I defined earlier, C. You multiply by the settlement. Settlement is 4 mm. If you should multiply the settlement, 4 mm is 4 divided by, you convert it to meters, is 4 divided by 1000. So that's why we have 0.004 here. So you have to add CA. A is the settlement. As you see, this large stiffness multiplied by this settlement, we have to add it at position 3, because we have settlement at the third degree of freedom. So we add C multiplied by this settlement at position 3. So if you run this code, we have this. We have this value, this added to this position. So these are modified false vector. So once you have modified the false vector, you can calculate your displacement vector Q. In my PowerPoint, I denoted as ds, but here I'm denoting as Q. So Q is my displacement vector. So you can say K, the inverse of K multiplied by F. Let me write it the normal way. So this is our displacement vector. At position 1, we should have 0. We have a support degree of freedom there. So it's supposed to give us 0. You can see it's give us a very, very small value. At position 2, we have is free. We have a rotational degree of freedom, and that rotational degree of freedom is given by this value minus 0.0007 radian. The value is in radian. The value is in radian. I think times 10⁻³ because I use kilonewton. But this is the radian value. These two are the degree of freedom at node 1. These two are the degree of freedom at node 2. And the last two is the degree of freedom at node 3. So once you have calculated the displacement vector, we can calculate our reaction vector R1, which I showed you in my PowerPoint presentation. Yeah, like this formula here. We use this formula to compute our reaction vector. Kk is our local displacement matrix, Sk is our displacement vector, our local displacement vector, Pk is our local force vector. So R1 is representing my reaction vector for the first finite element. So K1 is my local displacement matrix for element 1. So this is my displacement vector for element 1. I'm extracting the displacement vector of Q at position 1, 2, 3, 4. That's why here is 1 column 4. So minus P1. P1 is my force vector. So if we calculate this, wow, I got a different answer. Sorry, here should be negative. Why is here negative? Because the settlement is downward. So I think because the support moves downward. So I think that's why here is negative. So here should be negative, not positive. So how you modify your force vector with settlement, you subtract, you add minus C times the settlement value. Let me run again. When I run, you can see the reaction. These are the reaction values for the first finite element. The first two is the reaction component at node 1. Second is the reaction component at node 2. This 43.1348 kilonewton is what we have. Here. 43.133. Let me zoom in. Okay. 43.1338 kilonewton. And it is the vertical reaction at the support. Like here, you can see the value here for 3.14 kilonewton. Since we have a pin support at node 1, the moment will be 0. There won't be moment there, so that's why here is 0. You can see this 2 is the reaction component at the second node. The first one is the vertical reaction. That's the shear force at that point. 50.8662 kilonewton, and we see this here 50.86. We see this here 50.86 kilonewton. The moment at that node is 32.06. You see it here. Let's check it. We see 32.06. So the first two represent the reaction component at the first node, the last two the reaction component at the end node. So we use the same formula, K2, the local student matrix for element 2, the displacement vector for element 2. Just here we're extracting the displacement values at position 3, 4, 5, 6. So that's why this is 3 column 6. Choose our displacement vector. So you multiply this and you subtract the first vector from it, you will get your first vector. You get your first vector for final element, your reaction vector for final element 2. The first two is the reaction vector at the start node, the last two the reaction vector at the end node. This is 10.369 kilonewton. This is 32.06 kilonewton meter. This is 3.63 kilonewton. This is 0 kilonewton meter. So I can validate this result on the PowerPoint. So we have 10.337 kilonewton at the start node, which is what we have here. 10.37 kilonewton. At the end node, we have minus 3.63. Let's check. You see the value? We have 3.63. At the start node, we have a moment of 32.06. Let's check what we have on PowerPoint. 32.04 is 06. But yes, it's quite close. 32.06. At the end node, we have 0, which is 0 here. So this is how we use finite element procedure to solve beam problem. This is the only problem I'm going to use MATLAB to solve. This is the only beam problem I'm going to use MATLAB to solve. In my subsequent video, I'm going to solve this same problem using ANSYS in 3 methods, using the one-dimensional method, using the two-dimensional method, and also using the three-dimensional method. Thank you so much for watching my video, and I hope you understand the basic principle of finite element procedure the principle of finite element procedure applied to beam problems. Thank you. Have a nice day.